course, in 2050 to have carbon neutral food chain. We focus mainly on the thermal processes like the cooling, the freezing, and the heating. The scope of the project is post-farm gate, so from processing to the end user, to the consumer. The project is 4 years. We started in 2021, and we are ending the project now in September. We have 30 partners from 12 different countries in Europe. And because we are kind of soon finalizing the project, we also have many dissemination activities like this one and others as well, not only for Europe, but also internationally. The solutions that we are working within the project is to identify the greatest potential for reduction, looking at the different countries that are involved in the project. We also are developing, adapting, and applying new technologies that you will hear about today. And integration and streamlining of processes is also part of this. And of course, it's very important to demonstrate the technologies to stakeholders. It's highly technological, but we also try to bring in non-technological solutions. So this is the simple sketch of the food value chain, and it illustrates that we want to cover all parts of the food value chain from the processing stage. So not the farm stage, but everything after that. So for example, we have created technology roadmaps. We have almost finished all of them. And the last one is the processing technology roadmap that we are currently working on. So these roadmaps say something on how to reduce greenhouse gas emissions. You can find a lot of information of the different type of technology that is available for the different stages here. Some are similar between the stages, some are quite different also. One big part of the project is also the demonstration side, so the demonstrators. So we have 21 demo cases ongoing in the project. And it was very important for us from the beginning that we cover the whole of the value chain here, as shown here. So we have demonstrators from the different stages here that has a green ring around. And today you will hear from 3 of our demonstration sites, and they are all within the processing part. So the aim behind, we have several kind of ways of reducing greenhouse gas emissions, and I'm showing some of them here. So we're working with integration and optimizing of the energy flows, increasing energy efficiency, eliminating fossil fuels, and increase renewables. We're also working with improving processing and preservation conditions and reducing food waste. And of course, very central is also the use of natural working fluids and materials. We have a web page that we have worked with keeping up to date throughout the project, and we add information there continuously. If you either go to enoughemissions.eu, you can find it, or you can scan this QR code. In the top part of this is a screenshot of the website, but in the top part you can go and find more information. For example, you can find news and also upcoming events. We have some that will be open to public also to participate in. We also have publications there, quite many. We have the deliverables that are open there. We have some papers, we have fact sheets, and many other things. So please have a look there if you are interested in more details from the project. So that was a short introduction from me, and now you can hear from the different demonstrators in the project. Thank you.
Thank you, Christina. Thank you so much for setting the tone. For rest of our team members, I really, I am not sure how the word enough came about to be the name of the project, but it certainly puts a good thought in the process that nothing is enough, even if you have tried enough to reach where you want to do. So I think that's a great focus, and I think all members, and we have great numbers of participants here today. They would like to go back once you're free, gentlemen and ladies. You can access the IIR and you can access the Enough project page, and you will see that they are doing a lot more than enough. So thank you, Christina, for being here. Thank you so much. And now I will move to, I will move to Eric. Thank you, Eric, for being here. And Eric is also a researcher at the Sintef Ocean with the Department of Fisheries in Neo Biomarine Industry. Eric is working to improve the efficiency of thermal processes in the food industry with a focus on energy use, product quality, sustainability, and Eric is passionate about applying the digital and the innovative techniques, in which includes modeling, simulation, data science, and AI to drive sustainable change in seafood, fisheries, and aquaculture sectors. It's like I think he's the Eric is the most intelligent AI guy of all among us. So, and I don't know how he applies the tools of data and AI in terms of simulation. So I hand it over to Eric to you to walk us through in what you do. Thank you so much.
Thank you. Thank you for the introduction and thank you for the invite. I hope that you can hear me well and see the screen. If not, let me know.
It's good to go.
Yes, thank you. Okay, so I will spend a little bit of time talking about brine freezing of fish. But since we are talking about fish and fisheries, which is a domain that I work mostly within, I thought it would be useful to look at some of the background data. This chart here shows a global total production of farmed and captured seafood in 2022. And the total annual production then was 223 million tons. And this chart highlights that China is the dominant producer, but also that India here stands out as a significant contributor. So in comparison, Norway, which also is a country that has a long and proud history of capture fisheries and also aquaculture, together with the EU, we produce almost 9 million tons annually. I'm not sure about the exact division between farmed and capture fisheries in India, but looking at global numbers, around 50 to 60% of the seafood is farmed, while the rest comes from capture fisheries. And if you look at the global seafood trade, it is clear that there's a high level of exchange internationally between countries. So fish can often be farmed or captured in one region. It's then exported for processing in another country and could then also be redistributed as a final product in a third region. And Norway is a good example of this. We are a net exporter. That means that we export more fish than we import. So, for example, a large share of our farmed salmon is exported, and we export it gutted and whole to processing hubs in Europe. There it is filleted, it's portioned and packaged, and then it could be re-exported back to Norway and to other countries or sold domestically. So the key point here is that when you look at the map that you see here, with all the arrows, you see seafood going from place to place. There's a high interconnected nature in this industry. The seafood processing is global for sure. And it is crucial to reduce the environment impact of the production chains here. So transportation between countries accounts for a significant share of the total emissions. And if we look at air freighted fresh fish, this accounts for a large amount of the emissions. So a more sustainable approach is to transport frozen fish using low emission transport methods. So that's the topic of today. And when we look at freezing of seafood, there is many different types of equipment, but fundamentally 3 methods. First, we have air blast freezers. They rely on blowing cold air over the food to extract heat from the food. Secondly, there are contact freezers where heat is removed through direct conduction. This method offers excellent heat transfer efficiency as food is in direct contact with cold plates. And we often see that for fishing vessels, they employ vertical plate freezers, as you see pictured low on the right side. And then you have horizontal plate freezers which are suitable for filleted and carton packaged products. The third method, and my topic, is brine freezing. And I have these pictures here just to show that this is by no means a new method or a new technique. So when looking in literature, or you could almost say history books, you see that brine freezing was considered a modern method back in the 1910s, 1930s. It was then considered a modern method, which marked the beginning of the industrial fish freezing industry in Norway. So these pictures, they show various adaptations of brine freezing. You had the direct methods, which you see pictured on the left, and you had indirect methods, which you see pictured on the right here. These were popular methods, but as air and plate freezing the technology advanced, the brine freezing fell out of use, and today it's almost no longer in use in Norway, except for freezing of crabs. And the reason to look into brine freezing again is really simple, because on paper it compares very favorable to other methods when it comes to efficiency. One of the main advantages is that brine freezing has an excellent heat transfer because the food is immersed in liquid, so you have great contact between the brine and the food itself. Also, you have a very high heat transfer coefficient compared to air, especially if you have agitation in the brine itself. And this is what you see on the graph here on the left, that the heat transfer coefficient is comparable to that of plate freezers. Lastly, dependent on what kind of brine you use, but if you use salt brine using table salt, you will have typically operate at a higher temperature level compared to air and plate freezers. This is not favorable for heat transfer, but it's favorable for operating the refrigeration system. So basically it equals less compressor work. And that is also what you see on the right-hand graph. It's a theoretical comparison. Specific energy used for freezing 1 kilo of whitefish. Using brine freezing, it's almost half compared to a tunnel freezer. There are, of course, some drawbacks related to quality. The main issues that are identified is the salt uptake and also oxidation in fatty fish. In addition, working with brine, of course, requires some engineering. The systems and equipment must be designed to handle corrosion, and hygiene in brine, of course, must be carefully managed. But these are solvable challenges, and that is also why brine freezing has gained renewed attention recently. So previous studies in the last 7 years, it has been tested on whitefish, where it showed promising results when they looked at what kind of yield you could have in clipped fish or fillet production of whitefish. They also saw that freezing times could be 2 to 3 times faster compared to air. And also for pelagic fish, it was demonstrated that the specific energy use that you could get was really, really low. And that is also why we have this demonstrator in enough. So the demo 15, as it's called, it's focused on brine freezing. Energy efficiency is the main motivation to explore the method. And we had a company in Norway, MMC, they were involved. They manufacture and provide equipment for seafood industry. Together with them, we built a brine freezing rig. As you can see pictured here, it's just a rectangular tank where you have circulating brine going through and together with a refrigeration compressor here. We mostly used table salt brine solutions here, and we then operated the brine at -14. And we tested various applications on seafood for this. Perhaps the most promising concept was the two-stage freezing of mackerel. And the main motivation here was to reduce not only the freezing time, but also the energy consumption compared to the conventional method. And the conventional method is that you use large air tunnels. You pack mackerel in boxes of 20 kilos, stack them on trays, and put them into quite large air tunnels. There they spend between 18 to 22 hours to completely freeze the entire batch. Our concept involves pre-freezing individual mackerel before packing them into these boxes and completing the freezing process in these tunnels. And our preliminary calculations show that we could half the overall freezing time, and we could also gain an energy consumption reduction between 10 to 20%. So moving on to what we have done, what we have tested. We have done several trials actually. One of the first trials we carried out was to determine at which point should we switch from brine freezing to tunnel freezing. So for this we used a brine, operated it at -14, and we took 50 kilos of mackerel and gave it enough time to properly freeze in brine, single freezing. Then we took it out, immediately placed it in fresh water so that we can thaw it, and we monitored a temperature during thawing here. And the objective was to kind of locate, okay, what is the, let's call it the sweet spot? How much heat can we extract from the fish while maintaining enough flexibility in the tail so that we are able to actually pack the fish in boxes. And this curve then shows temperature from this first trial. This is temperature in a single mackerel. You have the core temperature, is the purple one, and then you have the tail temperature, which is the blue one. Those are the, let's say, the important curves to look at here. What we saw, it took about 120, 160 minutes to reach -14 in the core, looking at several samples. But we also see that the ice formation in the tail was quite more rapid and even faster than for skin temperature, for example. And then during thawing, we monitored the tail temperature, the blue curve here, and we took out samples at different times and measured the flexibility of the fish. So at -5, that is at -5 in the tail, the mackerel was still too stiff, so we couldn't fit 20 kilos in a box. I think we managed to do something like 14, 15 kilos, so that's quite a huge loss. So we took some more samples, and when we reached -2.7 in the tail, then we had a flexible enough tail so that we were able to actually pack these boxes with 20 kilo. And at this point, we saw that the core temperature was about minus 5.6 degrees. So the next trial was then to do a complete freezing cycle, pre-freezing in brine using the target temperatures that we just saw, and then completing the freezing in a conventional tunnel. And there were some challenges here that impacted our results, but this graph here still shows that the concept can significantly reduce the freezing times. If you look at the blue top curve, that is a control box. That's fresh mackerel, while our box, core temperature, is the purple one, the middle one. And we see that the fresh control sample, it took 16.5 hours to reach minus 18, while and that is near the surface, that is not the core temperature. While for our box of pre-frozen mackerel, it took about 13 hours to reach the same temperature. And that also includes a 3-hour hold-up in ambient temperatures, which, if it hadn't been for that, we could most likely see an even greater reduction here in freezing time. Yeah, so lastly, I won't spend too much time on this. We also did, based on these results, a theoretical evaluation of how much energy could then be saved using this concept compared to conventional method. And here we set that the transition point from brine to tunnels occur at minus 5 degrees, and assumed some basic COPs for tunnel freezers. We assumed a COP of 2, and we used specific energy use consumption for brine freezing that we found in literature. And the theoretical calculations show that you could save about 2 megawatt hours per 100-ton batch of mackerel. And this is equal to 14% savings, which is in line with the expected impact. And of course, is a significant number in energy reduction and therefore also emission reductions. So, yeah, short conclusion is that brine freezing is a very efficient method. What we see is that it's underutilized when it comes to seafood processing. Concepts on how to integrate them into current production chains must be carried out. And that is what we have shown in this demo. It's not a simple take out existing equipment and put in a brine freezing. You have to evaluate the entire chain and kind of develop the concept itself. And there are different challenges for different products. So for mackerel, we saw this flexibility in the tail, which is like a practical barrier. But the key point there is that they are all solvable, and the potential upside that brine freezing could provide, the energy efficiency, should be motivation to explore these solutions. And yeah, that is what I have to say. So thank you.
Thank you, Eric. That's great. And I will also now request our audience, if they have any questions, they can put into the QA box or the chat. We'd like to, I think, because each topic has its own merits, we would like to probably take the questions after the individual sessions. Eric, I have one or two questions, if it's okay, permitted to ask. So I think in the whole process of freezing fishes is also the most critical product is the produce, right? So the whole efforts in terms of preserving is for the produce. So in the apart from the the processes of temperature and the energy saved, in the real analysis of eating the food, I mean, like eating the fish after it's been processed in two different scenarios, is there a significant difference in the how the fish comes out to be on the plate in terms of taste, in terms of its flesh, in terms of its color, in the both processes of tunnel and or brine freezing?
We have not done studies in this demo on not on mackerel. We did some testing on salmon, And there we saw some sensoric changes. Basically, what I'm saying is that there was a color change when freezing in brine compared to air freezing. And that color change we could lead to, or could be negatively accepted, you could say, by the consumer. So for sure, different methods have an impact on the product quality, and this must be taken into consideration. It's not only about carrying out the process as efficient as possible. You also need to maintain and maintain the quality of the final product.
Okay, I think we have three questions. Before I come to that, I have one rejoinder question. Is that once we brought the fish core temperature to -14, then you put it back again to thawing for bringing it back to a much higher temperature. Um, is this a process to increase the quality of fish, or is a process that in the next phase of cooling down it helps you cool down much faster?
I should probably have made a comment there, but uh, the process of freezing down to -14 and then thawing again, it was purely for locating this sweet spot. In the real process, you would stop the freezing process at the point where you could just transfer it into the tunnel, because freezing and thawing, it's not efficient, and it's not good for quality.
Awesome. Thank you. So some quick questions. I have a question from Everett, and the question is there any data on salt take-up?
Yes, there are several studies on this for different species as well. Um, I'll let's see here. I had a slide on that. Salt uptake here. So yes, you must expect it if you don't have vacuum packing or some kind of barrier between the fish and the brine. You must expect salt uptake. But if you look at mackerel in our case, where you have the skin on and so, then the skin itself acts as a barrier. And also there are diverging results when you look in the literature. You have studies that they measure that there is a difference in the salt content when comparing brine frozen and plate frozen samples, but a taste panel could not detect that change in salt taste. So there is nuances here that needs to be investigated.
Okay, so we'll go to the next question, which says that have you tried to use slurry, which is ice slurry, in brine freezing, and what do you estimate with the benefits in terms of freezing time?
Short answer is no. We did not test brine freezing in this study. Yeah, no, we didn't.
Yeah, but it's just like a top of my mind thought, like if the process and the whole efforts we are trying to bring out is in terms of saving energy, then we actually have spent some energy in making slurry, and then again we are going to, have a differential energy being spent in terms of bringing it to -14 or whatever the sweet spot is. So it could be a good study in terms of seeing how slurry actually adds to the total value chain thought process. Sorry. The next question is, I'm sorry, Eric. So it says this from Dawn. It says, it seems you brine froze, then partially thawed. Did you try a shorter brine freezing process? I think you've already answered with warm brine. I don't know. Can you please, you want to answer that, Eric?
Did not test a shorter period, if that was the question. But
I think it's the same that probably I asked in a different format, but it says the same. So
yeah,
it says thawing. Would you like to use warm brine instead of like we have a differential water there? I think that's what you probably could be. So Don, sorry if we do not understand your question properly, but still, Eric, I will leave it to you to answer.
So as I was saying, in the let's say the real industrial process, we would not freeze and then thaw. We would stop the brine freezing process at the point where we could then transfer it and complete it in a tunnel. So yeah.
Yeah, great. I think the last two questions only I'll take with you, Eric, because otherwise we'll have a paucity of time. So there's the next question is, if you have salmon, you also add often salt before smoking. Uh, can this uh, can this drawback of salting by the brine be seen as a beneficial thing?
Yes, absolutely. And that's why I'm saying that we need to look at the concept from a product basis, product by product, because the salt uptake might be a drawback for some products, but it might be a benefit for others.
Okay, I think I have four questions, but I think we'll come back to the end of the session for rest of the questions. So, friends, if we have not, Eric has not answered, does not mean that we will not come back to you. We'll like to go further into the program. Please stay tuned, and we'll probably come back to these questions at the end of the show. Thank you so much. Before we move to the next speaker, our backend team says that our video to invite all our guests for RefCold is possible to play. So can you play our backend team if you can play that video, and then we'll come back to the next session.
Welcome to RefCold India 2025, South Asia's premier refrigeration and cold chain exhibition, an unparalleled platform where innovation meets opportunity. Experience the future of technology and innovation as global pioneers showcase groundbreaking advancements shaping the cold chain industry. RefCold offers a platform to explore advanced cold chain technologies across various sectors, including the food processing industry, pharma industry, transportation industry, last mile delivery services, hypermarkets, agriculture, horticulture, floriculture, and energy efficient cold storage industries. At RefCold India, we foster powerful government connections, empowering policies and initiatives to revolutionize the refrigeration landscape. Discover a world of possibilities at the International Pavilion, where global collaborations take center stage. Strengthen your industry ties through B2B meetings and Association Connect programs, forging partnerships that drive progress. Expand your horizons with knowledge sessions led by industry experts and micro-influencers, sharing insights to inspire, inform, and empower growth for all. RefCold India champions MSMEs, providing an international platform for their innovations to shine.
As many of you know, RefCold is a very important platform for refrigeration and cold chain industry. This time it's going to be happening in New Delhi. New Delhi is, the real hotbed for technology players. So I'm really looking forward to RefCold 2025, and I hope each one of you watching this video would also join along with me in RefCold 2025.
The cold chain industry plays a crucial role in preserving food and material when they are not required for immediate consumption. However, we face significant challenges. To tackle these challenges and seize new opportunities, we are thrilled to announce RefCold 2025, which will take place from September 18th to 20th in 2025. The location is Bharat Mandapam.
In the present scenario of what is happening in the development of cold chain in India, and RefCold being Southeast Asia's largest exhibition, it is going to be of utter importance for the people and the stakeholders to know what NCCD is going to do and how NCCD is unfolding its new developmental plans in the development of cold chain in India.
Join us at RefCold India 2025, where the industry's biggest players, brightest minds, and boldest ideas converge. Be part of the revolution. See you in Delhi.
Thank you, the backend team. Please give the rights to Sergio. Thank you, Sergio. We have now uh, a session on blast freezing with ultra low temperatures CO2 systems for meat, fish, fruits, and vegetables, and also for dairy. And I'm so honored to have Sergio Girotto. He Sergio, I think, is probably the most seasoned veteran. He was born in 1956. He holds a mechanical engineering degree from Padua University, and his professional career began at Nordica, which is a company producing plastic ski boots in Italy, where he worked as a designer for automation processes. From 1984 then onwards till 2004, he was a part of the Coston, a manufacturer of refrigerated display cabinets, where he held various roles within the technical area. His responsibilities at Coston included the lab for prototype testing, central after sales services, the refrigeration technical office, quality control, and the production of refrigeration units. In the last few years, he's been the technical and the R&D director and he's formed a company called the NX SRL, which is developing CO2 refrigeration units, and he's also the currently honorary president. I was given a much brief about Girotto, but I tell you, the kind of knowledge and kind of experience that he holds is tremendously huge. And over to you, Girotto sir, for the next session. Thank you so much.
Thank you. Can you see?
We don't see your screen, sir. Can you reshare again?
Can you see?
Not so far. Yeah, I think, yeah, it is coming on screen. Yeah, we can see your desktop, sir.
Okay. Okay.
Yeah, it's good if you can go in the PPT mode, so then we have just the complete screen for ourselves.
We have the double screen mode here, what we see.
Can you see better?
Yes. Can you check by changing slide, if it's okay for you to run? Can you go to next slide and then come back? Yeah, I think it's working fine. You can come to the original slide, sir.
Okay.
And over to you.
Okay.
Yeah.
The typical refrigeration, our duty inside the enough project was to a demonstrator for changing the refrigeration system with a natural refrigerant solution. Typically, we refer to a spiral belt system, which is mostly used for a lot of purposes. Before enough, we made in the same period of the start of the project, we made a first installation in Milano with a freezing tunnel for pastry with CO2 as a refrigerant. The design conditions were 38 air temperature and minus 40 evaporation temperature with a capacity of 160 kilowatt. This is a picture of the system, the spiral, the unit, and this is the P&I. Probably you cannot see the details, but in case I can share something. The problem with using the constraints of using CO2 was the management of the high pressure, the high discharge temperature, the high pressure ratio, and the work as we wanted to go down in temperature, the work down to triple point, close to triple point. The approach we used was a combination of field test with real systems and laboratory test rig to make it possible to experiment taking some risks in more severe conditions. The test rig we did was a cascade system with two possible way of feeding refrigerant. One was gravity feeding, and the second was pump circulation. The pump was a gear type with magnetic transmission of the power, the movement. The laboratory test rig was installed in our laboratory in Treviso, and as I said, was a cascade system. Here you can see some pictures of the system. This is the evaporator, the lowest part, and it was coupled with a chiller system. The test was intended for verification of practical aspects like discharge temperature and oil behavior, mainly these two effects. The first series of tests was made down to minus 50 evaporation, which correspond with air at minus 40 degrees approximately. We used the data test for preparation of a dynamic model. This activity was made by CNR, National Research Council, and we validated the model with experimental data, and there was a good correspondence between model and test measurement. The test was made down in the first phase, was made down to minus 50. This is the COP, obviously, on the only of the part related to the cascade system. A second installation made at the end of the project, toward the end of the project in 2024, was still in Milano, at design for heavier ambient temperature conditions, plus 40, and the evaporation temperature minus 42, with a capacity of 120 kilowatt. This was the same type of system. And in the end, after the successful installation of the second test rig, we wanted to explore more heavy operating conditions in our test rig. While the compressor envelope was able to run down to minus 50, we wanted to go down to minus 55, and we adapted the system for this operation. Here, the challenge was the high discharge temperature. We tested two configurations for the feeding of refrigerant. One was the circulation with pump, but we had a lot of problems. We fortunately was a test rig only, the pump was not reliable, and the reason was the low head of the refrigerant, the low net suction positive head. Probably it was much more than the manufacturer of the pump prescribed. While gravity feeding worked extremely well, and we completed the test with gravity feeding of evaporator, which is a problem in the sense that in a real system, we should install the refrigeration unit much higher than quite higher than the in level of the freezing tunnel. But we think it's not a problem due to the fact that in factories are quite high, so it can be at the moment an interesting solution. Last test was to identify, we worked very fine down to minus 53. We wanted to see what happens if by mistake we go close to near triple point. And what happens is, as expected, is that it is a stable condition because the ice formation takes a lot of time. And so working close to triple point is not an issue because there is the time to properly set and adjust the operation of the system. You see the ice forming. Excuse me. Conclusions are that the demo project was completed with success. We demonstrated the feasibility of evaporation down to minus 55, which corresponds to a water air temperature of minus 45. So the lower heat transfer condition can be compensated in part by a lower temperature. And we had at the same time a good result from the freezers using CO2 installed in the field. More systems are planned. We have a lot of requests. And this on the way, there is the challenge of feeding a real evaporator in a real freezing tunnel. Thank you.
Thank you, Giroto. That's a quick and nice presentation. There are again people, I request if you have questions, you can put on the question box. I have just one question to you. So since the Enough project is more about, conserving the greenhouse gases and energy efficiency, while it's a great achievement to reach to minus 55 on the CO2 system, but you said the testing was done at 40-degree ambient. At that point, is the system really efficient in comparison to other technologies or other refrigerants that are probably available in terms of energy consumption? While we may have achieved a good point in terms of CO2, but if you see the carbon footprint in terms of the energy consumed, will it be this still a winner, or will there be a downside to the experiment?
Of course, we have measured energy consumption, but the conclusions are that with going to minus a very low temperature, which is a demand request from the market, is possible in practice only with using CO2, because with ammonia we need to go to minus with very low suction pressure, and it is not probably a solution. Also, a direct system with ammonia is not good in the factories because there are people working. But nevertheless, the efficiency of a CO2 system, if properly done, is not that much different from in terms of efficiency from other systems. So I think CO2 in practice is the only solution with the natural refrigerants for a direct expansion for a freezing to a tunnel freezing system, and the energy consumption is not affected that much. Of course, it is a balance because if we want to reduce the freezing time, we need to go lower with evaporation temperature. Productivity requires a lower evaporation temperature.
Thank you. Thank you. I saw Armin, you raised your hand. Would you want to come in?
Yeah, just a comment. In some cases, as Sergio said, it is not desired to have any ammonia in the production site. And in some cases, a cascade system is a good alternative to have the CO2 system on the low side exposed to the production side, while you have the ammonia in the machine room. But in some cases, it is not possible to have this cascade system. And then it is, as Sergio said, the penalty on at the high ambient condition is relatively small compared to other refrigerants. And at the end of the day, these companies, they want to have a -50 freezing. That is what they're asking for. And CO2 can provide this in a safe way, and it has been demonstrated in many places now.
Awesome. So I have two more questions for you, Giroto. And I think the first I'll take looks very interesting because it comes from an anonymous attendee. So I am very impressed to have somebody as anonymous attendee. But anyways, nevertheless, the question, it says the system you designed operates across a wide temperature range from -50 to +40 degrees centigrade, resulting in a very large temperature lift. Given this extreme lift, why did you opt for a single stage vapor compression system instead of a cascade system, which is typically more suitable for such applications? Furthermore, considering that CO2 has a critical temperature of approximately 32 degrees centigrade, operating at 40 degrees would push it into the transcritical region. Would you please elaborate on the rationale behind the design choice? I am sure the anonymous is certainly a compressor manufacturer, but still I will hold on to that and go to you. Thank you, please.
First of all, the real system was a two-stage system, was a booster system. It's not a single stage, a two-stage. The intermediate pressure was about, intermediate temperature was about I would say -15, from -50 to -15. And the second stage was, the upper stage was from -15 to plus, I would say 80 bar normally. 40 degrees is an exceptional conditions in summer, extremely hot days, but it is rare. But in that condition, the system works in transcritical condition, which is not a problem. It's done in hundreds of thousands of systems, so it's not an issue. It's not affecting efficiency significantly because it is limited to, I would say, 50 hours per year. It's not a big problem, and the system works anyway.
Thank you. There's a great information shared by Alexander. And says that cascade systems with ammonia and CO2 are being used at -54 degrees for coffee drying. So thank you for that vital information. And then there is one more, I think it's more like a snippet, which says many sites also for food production prefer ammonia because you know when it is leaked out. So I think it's not a question, but it's like a sharing of knowledge. Thank you, team members, for sharing your valuable information. We'll keep the question and answer box open after the last session that we have with Armin. Thank you, Armin, for being here. And Armin is a great friend and a great soul. I really enjoy having small interactions with him. Professor Dr. Armin Hafner is currently a professor in refrigeration technology at NTNU, which is the Norwegian University of Science and Technology. And he also holds the position of the president of the Norwegian Society of Refrigeration and president of IIR, Commission D1. And Professor Hafner's education and experience include being a senior research scientist at SINTEF from 1997 to 2015. He also earned his doctorate, PhD from NTNU's Department of Energy and Process Engineering in 2003. And I would like to read about his thesis, which is very, very interesting, and which says it was titled "The Compact Interior Heat Exchangers for CO2 Mobile Heat Pumping Systems." And I think it's a great research that he's done. Jumping quickly to the topic that he's bringing to for all our benefits is the CO2 minus 50 degrees plate freezing technology. Over to you, Dr. Harman Hafner. Thank you.
Thanks, Ashish. Can you see me? Can you see the slide? Is it okay?
We see you and we see your presentation and we hear you nice.
Perfect. Okay. As we are a bit over time, I try to be compact. And thanks for having me here and giving the opportunity to talk about the plate freezers. This is our demo within the Enough project. You see it on the right-hand side. It's an automatic process facility normally where you use this. I will come back to that. We will share the slides here, so later on you can click through them on your own. Give you a short motivation, look a little bit into the system layout and some of the initial experimental results as well. So the method is to maintain the initial high quality of food and fish and most of it. And we know, as we have seen in the previous presentation, is very successful implemented to utilize CO2 in this respect. Also with the and this is very not likely to happen if there is a leak, if CO2 is leaking in a process facility, most of the food is not kind of being wasted, while you may have a challenge with ammonia if there is a leak. So with CO2, we can keep it tight. That is not a challenge, but it is also possible to go to this minus 50 level, which is very difficult with other fluids because of the density and the properties of the fluid, as Sergio nicely has explained in the previous presentation. Just a quick look into the PNID. The facility we're having is we have a centralized CO2 freezing plant with different suction lines at -8, -38, and -48 or -50, where we are going now. We do a subcooling device. I will explain it in the next slide. We do a capacity or measurement of the capacity by a mass flow meter of the supplied CO2 into the system. We have a liquid vapor separator to feed the pump, which was a challenge in the previous presentation. If you have enough liquid height or enough height from the liquid towards the evaporators, either thermosiphon, the self-circulation can be done, or pump circulation like we do it. Plate freezer on the lower right-hand side, where we measure a lot of temperatures, which we will come back to. So why do we do a subcooler? It's just also to increase the capacity, because if we then take the liquid, which comes with 14 degree, 50 bar, we subcool it to -33, then we are able to utilize much more of the specific cooling capacity, as you can see here. If I go just straight down from 0.1, it would be this specific cooling capacity. If I first subcool and then expand, I can more or less double nearly the cooling capacity. But of course, it needs a stage where I can remove this part of vapor or this part of the heat. So that's the stuff. So sorry for this coming in. Liquid separator is of course important, but also we need to have these CO2 feeding valves which supply the liquid into this separator tank, and we measure the mass flow rate, and that is part of the energy balance. Here you see the tank with a not insulated, before it was insulated, with some side classes and some liquid level safety switch to be able to secure operation. And on the left-hand side, you see also where we have some side classes to maintain liquid level and to see that we have a liquid level ahead, which is above approximately 4 meters. So this is 4 meters higher than the pump suction part, to make sure that we have enough head in front of the pump to avoid cavitation. So you see the pump now on the lower left before installation, doing the manufacturing of the facility, and the plate freezer with 4 plates, individual plates on the bottom part. I will show you where this is how they're normally operated. So with a hydraulic ram, you can lift and unload the plates. You put the product inside and then you close it. And with the contact freezing takes place while CO2 is evaporating within the aluminum plates in between the product. In the real system, as with our partner Demar in this case, you see how this is on board in a fishing vessel. In a larger fishing vessels, you see the people doing some cutting of different parts. It goes into the different processes, and to the lower side here, where I marked with the arrow, here you see 4 of these plate freezers typically in operation. So where they kind of continuously freeze the products. And which products? Well, most of it is whitefish, which has the highest product sustainability score. It's well suited for this. Boxes with fish, which are already pre-cut and filleted into these plate freezers, automatically charged and discharged on board. That's where these units are often applied. For other products, it's not so applicable. That's where the horizontal freezers and so on, the vertical freezers are taken. So this is just a picture of some samples we did lately with some different products, some herring, some salmon, and so on, just to show you what we did. And lately we also did a more scientific investigation with some apple juice as a dummy load, where we put these boxes, 2 boxes on top of each other, to have the possibility to put the measurement sensor between 2 apple juice boxes. So they are completely in the middle of the 2 boxes in a way as a sample. And you see on the right-hand side, we could maintain a CO2 temperature very close to -50. So the -50 was at the compressor, but of course, due to some pressure drop towards the compressor, this is what we got, close to -50. So 2 layers of apple juice, and then we measure in between, and we can see some differences in the measurement, and we investigate this, some different locations and so on, and you see that. And then we found out, okay, what is also very important, how do you really pack or wrap the products? And in this case, we had a slight difference here. Here is kind of a single layer of plastic on this part, while here you have a double or triple layer of plastic. And this had a significant impact, as you can see here on the locations. So without the double layer of plastic, which is just on one side, and it's not a very thick layer, but it significantly increased the freezing time. So this indicates really a lot how significant this packaging is on this kind. This just shows you quickly how the freezing capacity, of course, over time drops, because as more and more of the product is frozen, capacity goes down, just as an indication of how we measure this. In summary, the initial results were successful done on some dummy fish or some dummy loads and fish. Further results we will publish on our website, and we will also develop guidelines how to proper packing this stuff to make very homogeneous freezing, because we see a lot of impact on that. And if the upper plate has no contact with the product, is also a big challenge. So contact is important. Please visit the website that we will demonstrate, explaining all this in detail. And thanks very much. And as I said earlier, see you in Delhi in September. If you have any question, please, otherwise send us an email and we will answer them later. Thanks for listening. And if you have a question, please.
Thanks, Aman. Thank you so much. Again, I request if there are more questions, you can please put in the question box and we'll come and answer. Just one, Professor Aman, is it easy to conclude or good to conclude that between the 2 studies that we had between brine and contact plate, like plate freezing, for fillet, probably the way forward could be plate freezing, and for the whole scaled fish, maybe brine is the right solution. Is that a way forward?
Yes. And as Eric said, the combination is probably the clue to utilize the facilities in a way, if Eric says he can reduce the freezing time by half, it means they can double production. Because in that time when the fish is in the brine, the other one is in the freezer, and they can utilize the output can be double. That's the message also. With the simple addition of a brine pre-freezing, you can double production.
Thank you. And is this
Alex
also?
had a question, I think.
Yeah. I was gonna. Yeah, you can read that. You can read that.
Everybody can read it, and the answer is, I think it's not a question, Alex. It's a statement. That's also nice. Thank you.
Yeah. No, but I think the Q&A probably we can also read out for some people. But if everybody's okay. So there's one question from Don which says, did you control the hydraulic pressure on the package? That is the use of spacer to limit compaction of the packages.
Yes, Don, we did. We had some investigation there, but again, the mechanical forces are different because the cylinders are not, they're just at the corners. So at the corner side, it's a nice contact, but what we can see in the middle, there might be some challenges. So there's a lot of influence coming into this when it comes to really homogeneous freezing. It's kind of, we have to do some more work to get good guidelines.
Great. I don't see any more questions coming, but I will still keep this open for next 1 minute if there is. So there is one from, and his question says, is CO2 the best refrigerant, or there are any other alternatives to which have better performance for this process?
There might be no other natural working fluid, and the other alternatives are no alternatives because either they have a high GWP or they produce PFAS. And if we should avoid anything, then it's not to include anything which produce PFAS. And as Sergio said, and we can see the energy performance is nice, and the refrigerant itself is inexpensive, and you can get it even in India and else in the world. So it's not kind of dependent on any supply chain, which is difficult or costly. So that's also an important thing. I hope this helped you.
Yeah. Okay. And I think there is one. I think this will be the last question for the session. It says, any limitation on freezing time or crack of block due to too fast freezing?
Maybe Eric has an answer on that.
No, I think this is for the block. It must be for you because it should be towards the plate freezing. Any limitation on freezing time or crack?
Don't think so. We are still away from cryogenic freezing, which we have tested with salmon and so on before. So it's still -50, and it takes time, but it's still faster if you have the good contact and if the insulation, the block box material is not too insulating, then it works very well.
Okay, I think we do have one more question, but my apologies because I have exceeded the time allocated by our speakers. Thank you so much again in totality, the IIR team. I thank all the panelists today, Christina, Eric, Giroto, and Professor Armen. Thank you so much for being here and sharing the knowledge. And I'm sure the session has been very, very interesting. It has, kind of opened a lot of debates. And these are good, healthy questions that we are. So that means everybody's finding some sort of a connection to the efforts that are being put at the Enough project. We wish you all the best. And once again, like Professor Armen also supported, we'll request you all to be part of the show in India. Do visit. India is a very, very dynamic country right now in terms of the food landscape, and where we have enough to adopt good practices because our most of developments is happening now, and it's a time that we do not make mistakes that people learn over a period of time. So great interactions. Looking forward to all of you being here. Thank you so much for the wonderful session, and have a wonderful day ahead. Thank you so much.
Thank you. Bye bye.